So now let's look at one application. We're going to look at some molecules and look at the splitting patterns, the chemical shifts, integration, and we're going to use that information to determine which structure matches which spectrum. All right. So what we're going to learn is how to interpret spectra, how to match signals based on the splitting pattern and the chemical shift. And then also we're going to assign spectra to certain molecules based on the structural data. So here we have 4 molecules. When you look at them like this, if you're working on an NMR problem, the best way to approach it is to put the protons, show all of your hydrogens, right? So if you look at every molecule, you can see that I have all the hydrogens in and they're all color coded. And so we're going to look at a spectra and we're going to rule out each molecule based on what the spectra is. So 4 molecules, they all should be different spectroscopically, so they should all produce different spectra. And then we're going to match each one of these with a particular spectrum. So let's start with the first spectrum. So this is the first spectrum. And the first thing we want to do is count the number of signals. So if you look at this spectrum, you have 6 signals in this spectrum. And you can see that you have a signal here, 2 signals here, 2 signals here, and then 1 signal here, right just past 5. Right, and if you look at your molecules, the second molecule has too many signals, that has too many protons, so it can't match this spectrum. And then the other 2 molecules don't have enough. Each one of those has 5 signals. This spectrum has 6 signals, so we could rule those out. After we rule those out, what we're able to do now is focus in on this particular molecule here. Now we can go through and assign signals to each set of protons. Right? If you look at the integration, you have a signal down at 1 that integrates for 3 hydrogens, and then you look at the other signals. You have 2 signals just at about 2.4 and 2.7 that integrate for 1 hydrogen each. You have another signal that integrates for 1 hydrogen, and then you have 2 singlets, one that integrates for 2 hydrogens, one that integrates for 1 hydrogen. This is an interesting example because sometimes the OH and the NH2 protons don't show up, but in this particular spectrum, they do show up. So the 1H is the hydroxyl group. Notice it's at 5.1. And then the NH2 protons, that's the 2 hydrogens, right about 3.7. So we're not going to worry too much about those because number one, they don't couple to anything, they don't split, and then sometimes they don't even show up. Let's focus in on the doublet down at 1, and then the 3 signals here between about 2.6 and about 3.4. First of all, the doublet notice it integrates for 3 hydrogens, so it corresponds to the blue CH3. And the reason it's a doublet is because it has 1 neighbor, that teal proton. So N is 1, and so that signal is going to be split into a doublet. Let's focus in on this other section, right? Let's focus in on the sextet here that integrates for 1 hydrogen. That particular proton is that particular signal is going to represent the teal colored proton. You see it has 5 neighbors, 3 on the left, 2 on the right. And so because n equals 5, that signal is going to be split to a sextet. And then you have 2 signals here, each integrating for 1 hydrogen. And if you'll notice, the 2 hydrogens that are the red and pink hydrogens are indeed diastereotopic. We learned that in the last video, right? They're adjacent to a chiral center. The OH is a chiral center. And so those 2 protons are diastereotopic. And so if we look at the coupling or the splitting, you see that they're both split into doublet of doublets, right? The red hydrogen is going to couple with, or going to split with the teal hydrogen and the pink hydrogen. So N is 1 for the teal hydrogen, N is 1 for the pink hydrogen. And so that signal is going to be split into a doublet of doublets because all 3 of those protons are non-equivalent. And then by the same token, the pink hydrogen is going to split with the red hydrogen and the teal hydrogen to give you a doublet of doublet in that case. All right, so let's look at this next spectrum. You have 5 signals, and so that means that your molecule must have 5 sets of non-equivalent protons, right? So what can we rule out? We can rule out the other 2 structures, and so we're left with this epoxide and then the cyclohexenone derivative. But if you'll notice, in this spectrum, there are no vanillic protons, so there are no protons that there are no signals that would be representative of the 2 protons on the double bond, right? Remember, those protons show up between 4 and 6, and so we can rule that out, and we see now we're left with the epoxide. And if we look at the integration, we have a triplet that integrates for 3 hydrogens. We have a doublet that integrates for 3 hydrogens. We have a pentet that integrates for 2. And then we have a quartet and a pentet, both integrating for 1 proton. Let's start with the doublet that integrates for 3 hydrogens. That's going to correspond to the teal colored um, protons on carbon here. And the reason it's a doublet is because it has 1 neighbor, the red proton. So N is 1, N plus 1 is 2. And then if we look at the triplet that integrates for 3 hydrogens, that's the other CH3 because it has 2 neighbors, right? So N is 2 and N plus 1 would be 3. And then the pentet that integrates for 2 hydrogens, right? You have the green hydrogen on the right, you have the pink hydrogens on the left. So N in that case is going to equal 4, and then N plus 1 will be 5, so it'll be a pentet for those 2 blue hydrogens. And then with the red and the green hydrogen, uh, the one of those is integrated. One of those is going to be a pentet, and one of those is going to be a quartet, right? So you can see that the um, green hydrogen has 2 neighbors to the left, the 2 blue hydrogens, and it has 1 neighbor to the right, the red hydrogen. And so because of that, that signal is going to be split into a quartet because N is 3. And then for the red hydrogen, N is going to be 4 because it has 3 neighbors on the right and then 1 neighbor on the left. So that this particular spectrum corresponds to the epoxide. All right, let's do another one. Right, again, we can rule out the first molecule. We can also rule out the epoxide. And again, this particular spectrum has 7 signals, right? So we can also rule out the ketone, um, and that'll leave us with this molecule here, the alcohol, right? And so again, you see the OH proton kind of buried in there. I have an arrow pointing to it. We can just go ahead and discuss that. We know what that is, right? And then we have 2 triplets, both integrating for 3 protons. We have uh, 2 pentets, both integrating for 2 protons. Down in the far region, we have 2 quartets, and they both integrate for 1 hydrogen. So let's start with the 2 triplets. Both of those triplets are going to represent the 2 methyl groups, the CH3 groups, the teal group and the pink group. Both of those have N equals 2 for both of those. N equals 2 for both of those. And so because of that, they'll both be triplets. And if you look at the 2 pentets, you have both of those pentets integrate for 2 hydrogens. We have 2 carbons in the molecule that have 2 hydrogens on them. That's the red group of protons and the blue group. The group that is furthest downfield is probably going to be the group that's closer to oxygen. And then the group that's furthest upfield is probably going to be the group that's closer to bromine, just simply because oxygen is more electronegative. And so those blue protons are going to be more de-shielded, right? But you can see that for each one of those, N is equal to 4. And then so both of those are going to be split into a pentet. And then down in the far region, about 3.5, you have two quartets, and both of those quartets, we have the same scenario, right? The green hydrogen is going to be split into a quartet. It's probably going to be the one that's further upfield, right at 3.5. And then the yellow hydrogen is going to be split also into a quartet because N is 3 for that proton and N is 3 for the green proton also. So that is going to be further downfield, the yellow proton, because of the oxygen. We only have one molecule left, and that is the ketone. And if you'll notice, right, the ketone has 5 signals. The two protons on the double bond are different, and so they're going to give 2 different signals. That's what you see down between 6 and 6.5. You have a triplet that integrates for 2 protons at 3, and then you have down at between 1 and 2, you have 2 multiplets, both integrating for 2 protons. So if we zoom in on that area, we can see that um, the first signal is split into a pentet. The second signal is split into a quartet. Okay, so knowing that, we can pick out which protons those signals correspond to. So the quartet means that N is 3, right? And so if you look at the pink set of protons, it has 2 neighbors on the left, it has 1 neighbor on the right, so N is going to be 3. So the signal is going to be split into 4 lines, or N plus 1, right? And then by the same token, the pentet has, if a signal is split into a pentet, that means that N equals 4, right? So if you look at the teal protons, the blue protons on the left and the pink protons on the right, N equals 4 for that set. And so that signal for the teal protons is going to be split into a pentet. And then now we can look down at the signal that's at just past 3, and it integrates for 2 hydrogens, and it's a triplet. So that has to be representative of the blue set of protons, because if you look to the left, right, you'll see the teal protons, and if you look to the right, there are no protons on that carbonyl. Right, and if we go down to the further region, we see some complex splitting down here. The red proton should be simply a doublet because it only has 1 neighbor. That's the green proton. And then the green proton has a neighbor to the right, which is the red proton, and it has 2 neighbors to the left. But because it's not equivalent to either one, it's going to split both. So you're going to see a doublet for 1, and then you're also going to see another complex splitting pattern, and that's what you see here uh, for the green proton. All right, so that's NMR Assignment 2. If you have any questions, you can email me, and if you want to discuss it, we can even set up a virtual session over the break if you so choose. Got any questions? Just shoot me an email. All right, thanks.